All right, today we're going to pull back the curtain on one of Python's most powerful and, frankly, most used features, the dictionary. We're about to solve a mystery that pretty much every single Python developer has felt, even if they never really stopped to ask the question. And yeah, that's the question, right there. I mean, think about it. You can have a dictionary with 10 items or 10 million items, and when you ask for something by its key, it's just poof. It's there, instantly. How is that even possible? It feels like some kind of dark magic, but today we're going to see exactly how the trick is done. So to really appreciate this magic, we first need to look at the more boring ways of finding things. Because when it comes to speed, not all data structures are playing the same game. Look, if your data is in a list, finding something means you have to scan through it one by one by one. It's slow. A tree is a bit smarter, sure, it kind of walks down different branches, making choices. It's faster, but it still takes more steps the bigger the tree gets. But a hash table? Oh, a hash table is on a completely different level. It doesn't scan, it doesn't walk, it teleports. And this, right here, is the hero of our story today. The reason Python dictionaries are just so ridiculously fast is because under the hood, they're not lists, they're not trees, they're hash tables. This is the teleportation device that gives them their superpower. So what in the world is a hash table? Well, put simply, it's this brilliant way of organizing data that lets you just calculate the exact location of an item by looking at its key. No searching needed. You do a quick bit of math, you get an address, and you jump straight there. Okay, so teleporting sounds really cool, but how does it actually work? What's the engine making this happen? Well, it's a process called hashing, and honestly, it's surprisingly simple once you break it down. Let's just walk through it. It all starts with your key, right? You feed that key into this special thing called a hash function. It just crunches on it for a second and spits out a really big number. That's called the hash value. Now, that number is way too big to be a memory address, so we use a simple math trick, the modulo operator. You just take that huge hash value, modulo the size of your table, and boom, you get the final spot or bucket where your data is going to live. And here it is. This is the magic formula right here. This one little line of code is the entire engine of the operation. You get the hash of the key, you do a modulo with the size of the table, and that gives you the index. Simple, elegant, and unbelievably fast. But wait, here's a super important thing to get your head around. The hash value for a key, that's permanent. The hash of the string apple will be the same number today, tomorrow, and forever. But the final index isn't permanent. Why? Because the dictionary can grow, which means the table size in our formula can change. And if that number changes, the same key can end up in a totally different bucket later on. Now, of course, no system is perfect. Even our fancy teleportation device can run into a couple of snags. There are two main problems we need to think about. What if two different keys want to go to the same spot? And what happens when the whole thing just gets too full? Let's tackle that first one. I mean, it's bound to happen, right? The hash function, just by pure chance, might tell two different keys to go to the exact same bucket. So what does Python do? Does everything crash and burn? Nope, it does something really clever. This is called a collision. And when one happens, Python just calmly starts probing, which is a fancy way of saying it checks the next available slot in a predictable order until it finds an empty one. It's a simple but really effective fix. Now, I know what you're thinking. Wait a minute. If it has to check other buckets, doesn't that slow everything down? And the answer is barely. You see, Python is smart. It keeps its hash tables sparse, which just means most of the buckets are empty at any given time. So when a collision does happen, the probe is usually super short. It almost always finds an empty spot in the next one or two tries. The analogy here is perfect. Teleporting to the right neighborhood and having to check one or two extra houses is still 1,000,000 times faster than walking through the entire city. The other problem is resizing. When a dictionary gets about 2/3 full, Python decides it's time for a bigger house. It makes a whole new, larger table and has to reinsert every single item. Now, that one operation, that moving day, is expensive. But this quote explains it perfectly. Moving day is expensive, but most days are cheap. That one big cost gets averaged out over thousands and thousands of super cheap everyday operations. The average cost stays incredibly low. And check this out. You can see exactly how it works. On the left, with a small table of size 8, our key, the number 10, ends up in bucket number 2. But after Python resizes the table to size 16, the exact same key with the exact same hash value now gets a new destination. The math changes, and now it lives in bucket number 10. The key has moved, all because the table grew. It's totally predictable.
Okay, we've talked about teleporting, collisions, and resizing. Let's put it all together and look at the cold, hard data. This is the performance proof, the big O showdown that proves, without a doubt, why hash tables are the undisputed champions of speed.
And here's the evidence. This uses something called Big O notation to measure performance. Just think of it like a grade for how an algorithm's speed changes as you throw more data at it. A list gets an O of n, which means it gets proportionally slower the more stuff you add. A tree gets O of log n, much better, but it still slows down a bit as it gets bigger. But now, look at the hash table. For lookups, insertions, deletions, the average performance is O of 1. And O of 1 is the holy grail. It means constant time. And what that means is that the operation takes pretty much the same amount of time, whether your dictionary has 10 items or 10 million items. The performance just doesn't get worse as it gets bigger. That is the superpower. And what's really cool is this amazing power isn't just for dictionaries. You know Python's setObject? That's basically just a hash table with only keys and no values. It's why checking if something is in a set is also O1 fast. Same for other tools like collections counter. They're all built on this same incredible foundation. So let's bring it all home. The whole point of this explainer is to upgrade your mental model. So stop thinking of a dictionary lookup like scanning a list. From now on, I want you to picture this. You teleport instantly to the right neighborhood, and in the worst-case scenario, you might have to check 1 or 2 houses next door. That's the real speed of a Python dictionary. And that's the secret. It isn't magic after all, it's just brilliant, clever engineering called a hash table. It's what makes Python dictionaries feel so instantaneous. So now that you know how to teleport with data, what are you going to build? Thanks for joining me.